Hi everybody, welcome back to another video with Royalsoft games. So today we are doing chapter 4 of the Hitler book, and we will do one example problem of how to do a shear force and bending moment diagram. So let's start. Okay, so as you can see here, we have a beam that has two support. A support is a roller support, and for B is a pin connected. We can clearly see that from A through B there is a distributed load, and there are two free ends, and on each side there is a point load of 250 pounds. The distance from the free end to A is 4 feet, and A to B 6 feet, and B to free end 4 feet. So we can clearly see that this is a symmetrical beam, but for the purpose of this video we can approach it from symmetric way, but I will do it traditionally by cutting it through different sections with the equation, because I think in structural analysis what your professor wants to see is doing what I'm going to do. So the first step to attack this problem is drawing a free body diagram and finding the reaction. Okay, so free body. So we draw a free body. There is a 250 right here, a distributed load right here, which is 100 pound per feet, and we have a 250. And we know there is a AY, we know there is a BY. Since there is no force since there is no force in x direction, we know that sum of forces in bx is sum of forces in x equals to 0, and therefore bx is 0, so there is no reason to draw that. And one thing that this symmetric loading helps us is that we can right away calculate the uh, reaction. Since it's symmetric, we only have to calculate one side. So let's see. Okay, what we can do is I show you a trick. You can do the old way of finding the sum of moment at free end and doing the rest, but this way I show you it's better. So we know that this distance is 6 feet, right? So 150 times 6 gives you the direct point load for this one. So 150 times 6 is equal to 900, right? Half of this load is on this side, so if we cut it in half, so this half of 900 is on this side and half of 900 is on the other side. So what is half of 900? Half of 900 is 450, so we're only doing it for one side. So half of 900 is what? 450. And we have 250 going down, and this was going down too. So plus 250, since they're both going down, they're negative, equal to negative 700. So that means that AY is 700 since it's going up, and this forces BY to be 700. That easy. Okay, so now what we need to do is we have to cut this into different sections to find the shear equation and to find the moment equation. So the first cut we are going to do is from the free end right here. So we cut it, and then always when you cut something, draw the new free body diagram for it. So from here is what? It's 0 to 4. So we write 4, 0 less than x less than 4 feet. Okay. And then we come here, we draw the picture for it. So here, like that means we cut it. The beam, we have a 250 on it, right? And the distance from right here to here is x. We have a moment, and we have a shear. Now we have to develop the equation for it. So basically, sum of the force in y equals to 0. We assuming positive is upward. Negative 250 minus v equals to 0. This gives us that v is equal to negative 250 pounds. Now we have to find the moment. Sum of the moment at this location at x, positive counterclockwise, equals to 0. So moment plus 250x equals to 0. This means that moment is negative 250x pound per feet. So for 0 to 4, now we know both moment and V. V shear force is constant throughout, we can see. But for moment, what we can do is plug 0 and 4 into the equation, and we get the exact number for our bending moment diagram. Okay, now we have to decide where should be the next cut. The next cut is always on the next section of the beam. So we did from 0 to A, and right now we're doing 3N to A. Right now we're doing A to B. So this means that now we are doing 4 feet less than x less than 10 feet. Alright. And now we have to draw the free body for this one too. So the free body for this one is a little bit harder than the previous one. We have a 250 right here. And we have a distributed load, half of it, 150. We also have a 700. And this is 4 feet. And this is x minus 4. So this whole thing is calling x, right? This is 4, so this is x minus 4. This is very important. And so right here, the point load right here for this part becomes what? 150 x minus 4, right? And the distance right here, half of it, is what? X minus 4 over 2. Okay, now we have a moment and V. So that was for that, this one is for this. Have a moment and V. Okay, so now we need to do the same thing again. Sum of the forces in Y, upward is positive, equals to 0. So negative 250 plus 700 minus 150 x minus 4 minus V equals to 0. So V equals to 1050 minus 150x pounds. So now we have the equation for V. This time we have to plug 4 and we have to plug 10 into this equation in order to get the values for V. We can do also for the moment too. Sum of the moment at x equals 0. So that was our equation 1. This is equation 2, 3. And this one, now we're doing m plus 150 x minus 4. And the distance, as I said, x is 4 over 2 plus 250x minus 700 x minus 4 equals to 0, right? So m is negative 75x squared plus 1050x minus 4000, and the unit is pound feet. So again, this is another equation we have, equation 4. Remember, you can always pause if you can clearly see it and look at it when I review, when I stop right here. Okay, now we need to move on to the next cut. Okay, moving on to the next cut. So we can do the next cut from the other side's free end right here. This is easier too. Let's go. Okay. So now this time what we're doing is for 10 feet less than x less than or equal to 14 feet. You have to draw the free body diagram first. So we draw the free body like this. We want an M and V 250 pound, and we have a 14 minus x. Why? Because the whole beam is 14, right here is x, so 14 minus x. Okay, similar. Sum of the forces in y equals to 0, upward is positive. So V minus 250 equals to 0, V equals to 250 pound. Sum of the moment at x equals to 0 and negative m minus 250, 14 minus x equals to 0. So this means that m equals to 250x minus 3,500 pounds per feet. Okay, so this means that v is constant again right here, equation 5. And this means we have to plug the two value for it to find the equation. So for the purpose of this video, I don't want to hold you too much, so I will not plug the values right here in front of the camera, but I plugged the values before. You can check. So we will draw the SFD. So from 0 to 4, V was constant. So like that. Negative 250. Right? Right here is about 4. And then we go up. And then distributed load, it's like that. And distributed load went from 450 to negative 450. You can see 450, negative 450, and right here 10. Then we go up, then it was constant again, 250 and 0, 14. Negative, positive, negative, positive. Okay, see, we easily draw our shear force diagram. Now we're moving on to bending moment diagram. Bending moment is easier since we can see the shear and we can somehow do it graphically, but we still have the equation too, so it's easier. So from 0 we know it goes down, and we know it's a parabola like this, and then it goes back up. So this goes like this, and from the equation we know right here is negative 1000, negative 1000, location is 4, 10, 14, and 0. This is m x v x. There we go. We have our shear force and bending moment diagram created. Okay, if you have any question about this and you want me to answer, feel free to comment below. I will respond as soon as possible. And please watch our other videos. The link is above. I have a series of, if this is your first time watching my video, I have a series of mechanics of material. I have a series on static and a series of videos on structural analysis. I hope you learn what I'm showing you, because I'm teaching, but it was hard for me to learn while I was going to college. Thank you so much for watching this video and have a good day.